Hello, everyone. In this little presentation, we're going to be taking a foray into the world of the statistical analysis of test material. This is the first of a series of how-to talks, and we're really going to be just going into the shallow end of the pool on this one. We're going to be considering a couple of statistical procedures that are very easily implemented without any fancy equipment, without any advanced knowledge of statistics whatsoever, which are used primarily in evaluating achievement tests, including classroom tests, things that you might be writing for use in a class you're actually teaching. So I have naturally some slides ready to walk through with you. We'll demonstrate how to do this by hand, and we also will be having a look at how to operate within a spreadsheet environment if you have a larger data set. Okay, so then without further ado, into slideshow mode we go. Here we are. So the procedures we're concerned with have to do with what's called item analysis. And the underlying idea here is that when you create a test, you write test items, of course. So, you're teaching a course in developmental psychology and you want to write a test up or a quiz up on the subject of attachment. So you write a series of items that should, in theory, measure how well your students understand attachment theory and attachment research. That's the idea. The students who get more of the correct answers get higher scores and therefore are presumed to have learned more adequately. Now, the problem is that, okay, you sat down and wrote these items, but you don't have any actual evidence that item number 4 is actually helping you in any way. I mean, it could be that you wrote a wonderful item here that really separates, the grown-ups from the little kids, so to speak, but you don't know that. Chances are when you sit down and write a test, whether it's an achievement test or some kind of a measure of intelligence or a personality scale, at least some of the items you write are going to be no good. They're going to be bad items that if you are exercising due diligence, and especially if you ever want to publish this test or use it in a research or a clinical context, they're items that should be revised or eliminated. So how do we do that? That's the problem. And there are two different ways in which we could operate here. One is if you have some kind of external standard by which to judge the test items, in a way your job now is relatively easy. In other words, say it's an achievement test. If you already know these people are experts in the field, these people know next to nothing in the field, you can simply examine, how much better the experts do than the non-experts on each item, and only keep the items that really show who the experts are. Right? So you had known groups to begin with, and now you're using those known groups to construct, good test items that you can then use in future settings. This is great when you can do it, but in most everyday settings, we don't have that kind of external criterion. All we really have are the test data themselves. A bunch of people took the test. Here's how they did item by item. What am I going to do with that? That's what we're focusing on today. There isn't an external criterion. There's no standard by which we can judge the test items other than what's happening inside the test itself. Now, here we have to make a little bit of an assumption. We're going to assume that the test you created is not complete garbage. That on the whole, if there are, say, 40 questions on your test, that the sum of those 40 items does to some extent differentiate the more from the less able students in your class, or whatever it happens to be. So what we're going to do then is to create high and low groups, a group of those who are thought to be highly proficient, a group of those thought to be very weak in the subject, using the test scores. Now, skipping ahead a little bit, a couple of weeks, this is basically an approach that builds on the internal consistency principle. We're not covering that just yet, but that is what we're actually doing. We're looking for test items that cohere together, that hang together, and achieve a certain purpose collectively. Now, in doing this the easy way, there are two main statistics that we're going to use. They're useful and they're remarkably easy to come up with. One of these is called the item difficulty index. The item difficulty index, typically represented by a lowercase letter p. The only thing hard to understand about this one is that higher values of p actually reflect easier items. So it is measuring item difficulty, but in fact, it's low p values that would represent more difficult items. That's an easy confusion to fall into because you think, oh, it's high item difficulty, it must be difficult. And in fact, high index means low difficulty. All it really comes down to is this: what proportion, hence the p, right, of test takers get the right answer? Or put differently, what is the probability that a randomly selected test taker will get it right? So proportion, probability, percentage, call it what you will. So again, higher values mean it's an easier item. If the p value is 0.90, it means that 90%, 0.9 of the test takers got it right. And we'll look at how to calculate in just a minute. The other statistic is called the item discrimination index. Item discrimination index represented by an uppercase D, D for discrimination. What you're looking for here are items that successfully discriminate between or differentiate the high scorers from the low scorers. So to what extent does this item perform differently in such a way that if I'm well prepared for the test, I'm more likely to get the right answer than if I didn't prepare well for the test. This actually is the more important statistic of the two, in that, if D is very strong, you'll often be forgiving about less desirable values of P, although in an ideal test, of course, they're both going to fall within the desirable range. So how do we get it? Well, step one involves scoring the tests. So you score it item by item. Again, if I have a 10-item quiz for each person, I'm like, 1, you got it right, 0, you got it wrong, 1, 1, 1, 0, etc. You arrange the cases from the highest scoring to the lowest scoring. So you put them in rank order, and you just kind of put that all on a table. If it's a smallish data set, you could use a sheet of paper or graph paper for this purpose. Obviously, a spreadsheet will also do. The larger your data set, the more you are likely to really want to go into spreadsheet mode on this. That's the beginning. Now, step two, we've scored the test. We have our table showing each person, how they did on each item on the test. And now we're going to divide the sample into actually 3 subgroups, only 2 of which we're going to be concerned with, though. One group is the upper group, represented by an uppercase U. And ideally, this is about the top 27% of test takers. Why 27%? Some statistician wrote a cool paper back in, I think, the 1940s, in which he showed that this was the optimal cut point. There's no magic attached to it, and it's not mathematically required. If you happen to do it at 25% or 30% or 33%, it's not going to make a big difference. So you pick something that's pretty close to 27%, as your cut point here, and you go with it. Right? That's my best advice on this. The lower group, uppercase L, is the bottom 27%, give or take, of test takers. These should be the same size groups for the way we're doing these equations. So again, if you happen to go for what happens to be 30% in the upper group, it should be 30% in the lower group. But it's about 27% is where you're going to do the best job here. The middle group, you're going to ignore from here on. So it's, not quite half of your people are likely not to really factor into these calculations at all. These are the people who didn't do especially well or especially poorly, so they're less informative is the idea. Now, sometimes, like, what do you do if you've only got like 20 people in your class and you're like, well, yeah, 5 or so in the upper group, 5 or so in the lower group doesn't sound like a very stable statistical approach. Sometimes what people will do is to use what's called a median split, where you just, it's the top half and the bottom half, right? So you just split it right at the 50th percentile. If you're in the upper half of the test takers score-wise, you're in the upper group, lower half, you're in the lower group. That's okay. The problem here is that those ones in the middle aren't really that different. So the fact is, if I'm at the 53rd percentile and you're at the 47th percentile in terms of our scores, we basically got almost the same score. And the fact that I scored a little higher could even just be a random event. There's a couple of the bad items I just happened to get right and you didn't. So it means that you don't get as sharp a contrast. It's not as desirable. Again, the general idea is you want to compare a group of people who had high scores with a group of people who had low scores. That's what it comes down to. Now, the next thing is how many got it right within each group. So U subscript P is the proportion of those in the upper group who got the right answer. How many people in the upper group got it right? Not the proportion, it's actually the number, raw number here. How many got it right? LP, of course, how many people in that lower group got it right? So far, so good. So you have an upper group with a certain number of people in it. Of them, a certain number had the correct answer. That's the UP. You have a lower group, people who did not do so well on the test, and that's L. And within that group, a subgroup, L sub P, are those who did get the correct answer, even though they didn't do well on the test as a whole. That's it. Four numbers that you've had to get. If you're working with a small sample, you can just count them. I mean, it's like 1, 2, 3, 4, 5, 6, 7, and you're done. If you have a big sample with several hundred people in it, counting by hand gets not only tedious, but you're also somewhat error prone. You're better off do it using a spreadsheet and just punching in a function to do the count. I'll show you how to do that shortly. But that's it. We have 4 statistics then. And those are the only numbers we're going to need in order to derive item difficulty and item discrimination. How many people in the top group? How many people in the bottom group? How many of the first bunch got it right? How many of the second bunch got it right? End of story. So the item difficulty index is, again, what proportion of the test takers produced the correct response to that test question, that test problem. P is equal, therefore, to the sum of those in the upper and lower groups who got it right, UP plus LP, divided by the sum of all the people combined in the upper and lower groups. Obviously, the maximum value here would be 1. If everybody got it right, then if we have, say, 10 in each group, you have 10 right plus 10 right is 20, 10 plus 10 in the denominator is 20, it's 1. So a 1.00 means you have an item that was so easy that everybody got it right. The lowest it can possibly be is a 0, and that's what would happen if no one got the right answer. So you have, UP is 0, LP is 0, but you had 10 and 10 people, but 0 divided by whatever it is going to be 0. Clearly, neither of those extremes is going to be a very useful test item. In fact, it has no value at all because it's, all it's saying is, yeah, everybody knows that, or yeah, no one can do that. But that's it. So here is an example I'll walk through with you of calculating it, and then I'm going to show you another and give you a moment to sort of set the problem up on a piece of paper or mentally and walk through that one with you purely verbally. So suppose we have a sample of people who've taken the test such that we have 30 people each in the upper and lower groups. which means we probably had a little over 100 people take the test overall. But we don't need, again, we don't need to worry about those ones in the mid-range. And suppose that 25 of the 30 in the upper group had it right, and 15 of those in the lower group had it right. So how difficult was the item? Well, P is equal to 25 plus 15, which is 40. That's all the ones in this subsample who have it right, divided by 30 plus 30, or 60. So 40 over 60, or 4 over 6, is equivalent to 0.666, et cetera, or round off to 0.67. So that's saying is that roughly 67% of the test takers get the right answer. That's it. Now, here's one for you to at least begin to set up. So we have a slightly larger sample with 40 people each in the upper and lower groups, right? So that's U and L. And you have 35 out of the 40 in the upper group getting it right, 20 out of 40 in the lower group getting it right. So what will P be? Again, probably some people watching this have solved it either in their heads or on paper or with a calculator while I'm talking. But it's fine if it takes you a minute longer. Now we can just walk through it. The numerator of the equation is going to be 35 plus 20, right? Or 55. The denominator is going to be 40 plus 40, or 80. So what we know is that 55 out of 80 got it right. And so if you divide 80 into 55, you get a value that's about 0.69. It's 0.6875 to be precise. But now for that step, unless you're very comfortable with long division, do use a calculator. If you're very uncomfortable even adding, feel free to use a calculator to add 40 and 40, right? But it's about 0.69 would be the correct answer here, or 0.688 if you want to be a little more precise. That's it. Now we have that number. What does it mean? Like, how do I interpret this thing? So, like, how difficult should an item be? The answer is, it depends. So there's no math at this point. This is now conceptual, it's evaluative in nature. One thing it depends on is what we're using the test for. What are we using the test for? In some cases, you're figuring that most people are probably fine, but there might be a few people who haven't mastered what's supposed to have been learned in the last quarter and are going to need some remedial work. In some other cases, you might be looking to identify, again, just a few people, but it's a few who are way ahead of the pack and should perhaps be skipping a quarter or placed in a more advanced section, right? Those situations happen. More often, what we're doing is dealing with, a mixed group of people who are likely to be quite variable in terms of how well or poorly they've mastered whatever it is we're hoping that they are learning. And we want to sort them out. And, for example, for assigning grades or for deciding, which of several options they're going to go into next. That's the really standard situation, right? Like a regular classroom. Right. So, okay. Oh, important point here. You'll see this from time to time with tests that we're studying or using as examples. There's a kind of scaling known as Gutman scaling, named for Gutman, of course, probably Gutmann originally, where intentionally you start with items that basically almost everyone's going to get right, and you make them become progressively more difficult as you work your way through the test, so till you reach ones that virtually no one gets right. That's a special case, and some of the implications are a little different. So, okay, how difficult should an item be? Now, we're assuming we're talking about a mixed group of people, some high, some low, many in the middle in terms of their proficiency. It depends. What it depends on now is this, and put your thinking cap on. How many possible answers are there to the question? Not correct answers. We're assuming there's one correct answer, but how many possible answers could you offer? Now, at one extreme, consider the open-ended question. If I asked, say I'm doing a literature test or something, and I say, who wrote Tess of the D'Urbervilles? Now, there is not perhaps an infinite number of answers to that, but for all intents and purposes, it might as well be infinite. And I could name any name that any human has ever had. I could make up names that no human has ever had, right? And offer it. Now, granted, there's only one correct answer, but I have lots of options. So I'm very, very unlikely to land on the correct answer just randomly. In fact, it's almost inconceivable that that would happen. In this sort of situation where you could give any of, scores or hundreds or even thousands of possible answers, the optimal level for the item difficulty index tends to be about 0.5. For about half get it right and about half don't get it right. There's a lot of play around that. So generally anything within 0.1 of that is going to be considered optimal. So anything from about 0.4 to 0.6, you're probably in the sweet zone here. Yeah, it kind of makes sense when you think about it. If about half get it and about half don't, that's splitting the group in half, isn't it? So you're really differentiating, an upper from a lower group. But the fewer options you have, the more likely it becomes that you will get the right answer through chance alone, through pure guesswork. So at the other extreme, what about a true-false item? True or false, right? George Eliot wrote Tess of the D'Urbervilles. Now, assuming that you know nothing about 19th century literature, what are your chances of getting that right? You should have immediately said 50-50. If you didn't, you just weren't reflecting on it very carefully, because there are only two possible answers. You're going to give one of the two answers. If you don't know the correct answer, you're going to 50% of the time, you're going to get it right. By the way, that's false. It was Thomas Hardy, but that's neither here nor there. Now, a very common scenario is, of course, the multiple choice test. These can have 3, 4, or 5 options. Most frequently, we use 4 options, just kind of a convention. There's no reason that that's better than 3 or 5. In fact, it's not, but we tend to go that way. On a 4-option multiple choice test, the ideal hovers around 0.74. That is about 70-75% of the test takers getting it right seems to be the midpoint of the sort of sweet zone. Now, again, there's some play around that. So the value could be in the low 60s, 0.6, 0.65. It could even go up into the low or mid 80s, conceivably. Again, the reason for this is, well, go back to the true false for a sec. What if half the class gets the right answer on a true false question? Think about it. Half the class got it right. How easy or hard was that item? Now, again, if you reflect for a moment, or if you have just a very quick intuitive cast of mind, you'll recognize that that was an extraordinarily difficult item. It was an item that nobody knew the answer to, because half getting it right means that everybody guessed. So item difficulty of 0.5 would not be optimal. It would be brutally difficult. What you're looking for is somewhere in between that and the item that everybody gets right. And the mathematicians have worked it out for what the optimal place is for 2, 3, 4, 5 options. We don't need to know all of them, but since we use a lot of these 4-choice multiple choice exams, this is an important one. Okay, so that's item difficulty. Item discrimination is no harder to calculate. Here's the formula. D equals U sub P minus L sub P divided by U. In other words, if you're well prepared, if you're in the upper group, how much more or less likely are you to get the right answer than somebody who is ill prepared, who's in the lower group? That's it. The only thing that makes this the least bit difficult is remembering that you're dividing only by the number of people in one of the groups, not the sum of both groups. This one has a little somewhat different properties in that you can get negative results. So if, for example, no one who did well on the test gets it right, but everyone who did badly on the test gets it right, that would be a value of -1. That would be like the exact opposite of what you want the test item to do. In general, negative values are bad news for the obvious reason that it means that the better you prepared, the worse you do on that test item. How can that happen? Let me use an example of a kind of test item that some of you may even have seen in a class, psychology class. You're asked, who was the first experimental psychologist? And you have 4 options. And, they didn't include Sigmund Freud, which is often there as a lure for people who aren't well prepared, but you have Wilhelm Wundt there, and many of even the students who didn't prepare very well knew that was going to be on the quiz, so they get Wilhelm Wundt. But some of the very studious and bright people in the class notice that another of the options is Gustav Fechner. Now, the ill-prepared students totally skipped over his name in the textbook, but the ones who read it carefully recognized that Fechner, who was a little before Wundt, was conducting experiments in what we would now consider to be psychology. So some of them are like, "Ooh, is it a trick question?" And they put Fechner. And they're wrong because the person writing the test was really asking for who is generally considered to be the founder of scientific psychology, which is Wundt. You see what can happen. That's a poorly worded item that has misled people who are better prepared. That would need to be modified or eliminated. What you're looking for, of course, are positive values here. Here's an example of how we'd work it out. So again, it's the same as the one I did before for item difficulty. And you might recall that it was item difficulty index was about 0.67, which would actually place it in the happy zone if it's a multiple choice test. Not too far off if it was an open answer one, actually. So now we're going to get item discrimination. So it's UP 25 minus LP 15, which is 10, divided by U, which is 30. So 10 over 30 gives us 0.33. Ta-da. Again, we'll look at the other case we have, the one for you to set up. So what is the item discrimination index? What is the value of D? That should be a D here. I just realized that, sorry. What is the value of D for this item? Right. So as you set that up, what you'd realize is, well, UP is 35, LP is 20. So in these parentheses, we're going to have 35 minus 20, 15. U is 40. So we have 15 over 40. And again, checking my cheat sheet here, that gives you a value of 0.375, or about 0.38 if you want to round it to 2 places to the right of the decimal. So there's the value. Now, interpreting it, like, okay, I have values like, 0.38 or 0.33. What do I do with them? The bottom line here is very straightforward. Higher the better, right? We want a high degree of item discrimination. Frequently, test developers recommend a threshold for most purposes of about 0.3. So both of the examples we looked at cross that line. They would be considered good items from the standpoint of item discrimination, as they were from the item difficulty standpoint. Now, there is an exception here. If values of P are very high, if we're looking at really easy items, you reach a point where it's actually literally impossible to achieve discrimination of 0.3 or better. So if you're going to let some easy items into the test for whatever reason, if they're coming up with values of 0.2 or thereabouts, that may be as good as it gets, and you're going to keep it. Raises the question, why put super easy items on the test that aren't doing a whole lot of work for you? The main reason, honestly, if this is a classroom test or even a formal achievement test, student morale, test taker morale. We've all had the experience, I'm sure, unfortunately, of walking into a test, looking at the first item and going, uh-oh, oh no, I'm doomed. That's a terrible experience. It's also bad because if that happens on the first couple of items, we become demoralized potentially and perform less well than we could on the rest of it. We'll be like, oh, I don't know any of it. Circle things randomly, hand it in and run home and cry, right? Very few of your professors or even your elementary school teachers want that to happen. So what they'll often try to do is to have a few of the relatively easy items at or near the beginning, and maybe sprinkle a few through the rest of the test as well, so that even if you're not that well prepared, you're not having the experience of, I can't answer any of this stuff. There's a good reason. Also, I should add, if, multiple choice, if around 0.74 is optimal, that means if your whole test centered on that optimal zone, the average student would get a 74, which is a low C. There's nothing inherently wrong with that. A C is supposed to be an acceptable grade, but as we all know, there's over the years been a good deal of grade inflation. And if the average students getting C, C minus, C plus, that's going to feel kind of demoralizing also. They would hope that the average would be more like maybe a B minus to a low B rather than a low C to C minus. There we go. Do remember, D is more important. And again, there's no optimal range. So it's not like, ooh, it's not, it's 0.6, that's too high. No, 0.6 is great. The higher, the better. Now, I just have a few more remarks about this, and then we are going to have a look at a couple of spreadsheets just to see how else this can be worked with. It is true that there's a different way of calculating D if you have an external criterion. We're not going into that, but you can look it up. It's a different formula that gives you somewhat similar results. There's also a different formula if the upper and lower groups are not the same size. It's more complicated, and again, we're not going there, but if you need to work with that, you can find this information. As we do move ahead and study reliability and internal consistency, you'll realize that we can actually use something called a corrected item total correlation instead of the old D statistic, and many tests nowadays will do that. And if you have access to statistical software, it's pretty easy to generate. The results will be pretty comparable in terms of, almost identical really, in terms of which items you keep versus discard or modify. Now, one more thought about P. Sometimes you just put the whole sample of test takers in, throw everybody in. It's like, how many got it right? What's the P? Nothing wrong with doing that. Just be clear that that's what you're doing. And again, these specific procedures, P and D, are mostly used with classroom tests and or standardized achievement tests, not with other kinds of tests. They're very easy. That's the big pro here. There are other ways of accomplishing the same ends, especially substituting item total correlation for D. But when you don't have access to the fancy software, just make life easy on yourself. And that's it for that slideshow. Now, I do want to share a couple of little spreadsheets with you. So here's one which is actually sometimes posted to my class for practice purposes. It's simply analysis of how a small group of students did on a multiple choice test or on the multiple choice part of a test. And so we're just going to pick out one item here. Let's say we pick item 9, I09. So each column here represents one item on the test. Each row is one student, right? So here and the students are arranged in order from the highest to the lowest test scorers. All right. So we have a total of 21 students in the class. So, U and L would be around 5 or 6. And let's just say 6. So 1, 2, 3, 4, 5, 6 people. On item 9, U is 6 always for every item. On item 9, we can count how many got it right. It happens to be 6. So UP is 6, U is 6. Now we know that L is also 6 because that's we're saying 6 is as close as we're going to get to 27% of 22 people. So I just kind of paint over those. And again, this could be done with this size data set. You could do this just on a sheet of paper. So we have these 6 people. Now, how many of them got it right? 1, 2. So I have U is 6, L is 6, UP is 6, LP is 2. If I wanted to set this up, then I would say, okay, the item difficulty is 6 plus 2 in the numerator, UP plus LP, divided by 6 plus 6, or 12 in the denominator. So 12 goes into 8. Again, it happens to be about 0.676. Once again, that's just coincidence. If I wanted the item difficulty index, it would be 6 UP, right? That's how many of this group had it right, minus 2, how many in this group had it right, which is 4 divided by 6, which again happens to work out to 0.667, more or less, which is a very high level indeed. Now, I did also work this out using the spreadsheet, but I want to show you how to do that on a larger data set. So I'm stopping that share, going into this larger data set, which we'll be working with on and off for a while. This, again, is organized such that each column of numbers represents one, or each column rather represents one item on the test. Each row represents one person. Unlike the previous data set where we had only 22 students, the students in a section of an undergraduate psychology class, here we actually have 730 people. It starts on row 2 because I had headings in row 1. So it's 730. So it's a much larger data set, and not one where you're going to want to be counting by hand, because your upper and lower groups here are going to be about 200 in each, and you don't want to go through, 1, 2, 3, 4, 5, 6 to 200. That's just going to be insane, especially when you have 30 something items on the test. So what we're going to do is look at how to calculate this using the spreadsheet. And I'm doing this, I noticed I have done some of this already, but I intentionally deleted some just so I can show you how it works. The data set posted to the class Moodle, by the way, does include the syntax on how to do this. So to get the upper group, all I really need to do is to count. So we'll use the command count, and I need to count those in the column I'm in, which happens to be column Q, from row 2 through row 201, because I want 200 people. And I did something wrong. Let's see. Oh, Q2, you see what I did? Through Q201, my mistake. Spreadsheets at least tell you did something wrong. They don't always tell you how to fix it. For let's see, 32, okay. For the lower group, I could say equals count, and we're going Q 532 to 731. Again, I know I want 200, so I'm just, whoops, and I did the same thing again because I'm talking while I'm typing. And there we go. So we have 200 in each group. And again, that's going to be the same for each one. As a result, I might just not want to keep typing the equation over and over. Instead, I'm going to do this thing of painting over the remaining blanks and going to the upper right-hand corner here where there's this lovely fill command, and I'm going to fill to the right. And what this does is to replicate my equation intelligently into the subsequent columns. By intelligently, I mean that we went from Q to R to S to T. Now, to get UP, since it's 1 or 0, and 1 means the right answer, all I need to do is say the sum of Q2 through Q20, whoops, Q201, and it happens they all got it right. And for the LP value, all I need to do is to get the sum, add up Q532 to Q731, boom, and it's 153. So you'll notice that here, people in the upper group, the high test scorers, all have it right. This is UP here. Whereas in the lower group, the ones who did the least well on this particular test, 153 have it right, 47 have it wrong. Now to get value of P, I'm going to be saying, all right, well, let's just create the equation. So I want to take UP, which is Q738 plus, notice how it highlights the cell that I just specified. So that's a way of double checking that I'm getting the right cell, plus Q739, highlights that one, divided by the sum of, notice you have to use parentheses to specify that you want to do what's in the parentheses first. Now we're back to Q735, the upper group's total, plus Q736, the lower group total, and there it is. So the item difficulty for this item, number 12 on the test, is 0.88, meaning that 88% got it correct, which makes it a pretty easy item. This is a multiple choice test, so it's a pretty easy item, though perhaps not excessively so, given that this is one of those tests where the items start very easy and get harder as you go along. So if you look at the first few items, you'll see that essentially everybody has them right, literally everybody in some cases, whereas as we go further to the right, and it keeps going, it gets harder and harder. For item difficulty, what I want is to take the number in the upper group who have it right, subtract the number in the lower group who have it right, and divide by only those in the upper group. So you see, I've typed the equation into the cell. It appears also up here. Whenever you return to that cell, you'll see the equation again. We hit return and we get a value of 0.24. Again, notice this cell visibly says 0.24, but if I click on it, I can see up here in the formula bar what's underlying it. It's not actually the number 0.24 entered into that cell, it's this equation or formula. Now notice that's below our threshold, isn't it? But also notice that the item did as well as it possibly could. For an item that's that easy, where only 12% get it wrong, the best you can do is all the top people get it, and only some of the lower group fail on it. So actually, that's a pretty good item it's as good as it possibly can be if you want to have items that are that easy on your test. Now, again, we can quite easily use this handy dandy fill feature here, fill to the right, so we don't have to type the equation over and over. You'll notice just eyeballing this that they're starting to get a little more difficult. So even a few of the people in the upper group are now getting it wrong. And they're also getting considerably more difficult for those in the lower group. So we kind of expect that the values of P are going to be getting lower, and the values of D on the whole should get a little higher if they're good items. And they are. So here with items 13, 14, 15, we're in what for a classroom test would be considered kind of the sweet zone for item difficulty. We're also looking at items that do an excellent job of differentiating high scorers from low scorers. And so for example, looking at item 15 here, 196 out of 200 high test scorers got it right. So it's very unusual for someone who's good at whatever this is to not get it, whereas only 91 out of the 200 low test scorers get it right. Literally, fewer than half of them are going to get it, even though it's multiple choice and they have a 1 in 4 chance of guessing it right. Fewer than half are getting it right. So it's doing a very fine job of discriminating the two groups. Just to show you as we move further to the right, you'll see that the difficulty does on average continue to increase with a couple of blips where you have one that's harder than it's supposed to be. It does continue to increase, but the ability to discriminate also stays very strong for quite a long time here. In fact, all the way up to the end, where you have items that are so difficult that it's basically looks random. 1 in 4 should get it right by guessing, though in practice, it's the case that while some of the close to half of those in the top group are getting them right, nobody in the lower group is succeeding. This is a very carefully developed, professionally developed test, by the way, not just a classroom exam. So that was our lesson. You, again, may use this at will, and we'll say good day for now.